Hi, everyone. Welcome to the Siemens and NVIDIA live stream. We are here at DAC in the Siemens booth. I mean, first of all, this booth is incredible. And I am joined today by two very special guests. My name is Tiffany Jansen. I'm a software engineer and founder of Tiffin Tech. And I'm here with Amit Gupta. How are you, Amit?
Good. How are you?
I'm doing great, thank you. Amit is the VP and GM at Siemens EDA. And I'm also here with Tim Costa. Tim, how are you?
Doing great.
It's nice to see you both. And Tim is the VP and GM for industrial engineering at NVIDIA. Now, before we get into this conversation, which I'm really looking forward to, I want to give our viewers some background about what we're going to be speaking about today and what was recently announced. Siemens and NVIDIA are enabling the AI factory of the future from chip to grid. They are bringing AI to the physical world, bringing the industrial AI operating system that is redefining how industries design, build, and operate. So earlier this year, for anyone who was either at CES or tuning in, Siemens and NVIDIA announced something really interesting. It was both Siemens CEO Roland Busch and NVIDIA's CEO Jensen Huang were sharing the stage. And something Jensen said during that conversation really stuck with me. And I think it's a good quote to really lead into this conversation today, which is the goal of an engineer is not to write Verilog. The goal of an engineer, of course, is to solve problems and imagine great solutions. So I think that really sets a tone for this conversation. And to start with, Amit, I'd love to hear from you more about an overview of this announcement and what it really means.
Yeah. Thanks, Tiffany, and thanks for including me in this talk. So at the Consumer Electronics Show, Roland Busch, our CEO, with Jensen Huang, announced AI native chip design, and what that involves are really three pillars. One is faster engines. So how can we speed up the core software electronic design automation tools in order to give results faster? And there's two ways that we're addressing that. One is through GPU acceleration, and the other is through AI techniques under the hood of our tools to speed up the engines themselves. The other area was around smarter execution and trusted outcomes. So how can we now make the engineers as well more productive? So not just at the tool level faster, but making the engineers more productive. And that's all around developing out agents to now run the tools and be really partners with the engineers to be able to complete design tasks, verification tasks, sign-off tasks for semiconductor design and for printed circuit board design. So across that entire flow. The reason this matters is because semiconductor design costs, is extremely expensive. So cost of failure is very high in the order of tens of millions of dollars. So being able to have fast engines, fast EDA tools combined with productive engineers really unleashes a whole level of productivity.
Absolutely. I love how you phrase that. The agents are partners with the engineers. And I'm sure even since the announcement, your engineers, even yours too, Tim, have really been excited about this. And I'm curious to get what their reactions have been.
Yeah, I mean, from our vantage point with our customers, there's a real interest and demand and excitement over what capabilities are getting unleashed now with agentic AI. There's been a focus for the last 30 years in electronic design automation around faster engines and getting engines to be 2x faster every few years, and being able to use various techniques to speed up the engines. But this is essentially a new superpower that engineers have themselves to be able to improve the productivity. And it's across the entire semiconductor printed circuit board design flow. So digital verification, high level synthesis, custom IC design for test, place and route, physical verification. So across all those different steps, the opportunity and the ability to use natural language as a prompt to be able to say, this is what I want, and then have the agent be able to run the tools themselves autonomously, self-verifying, of course, across the engines to be able to come out with results. That's really the focus of what we've been doing. Still focused on making faster engines, of course, but also adding this new layer of agentifying the workflows, and very much partnered with NVIDIA in achieving this by using the NVIDIA AI infrastructure libraries and working with NVIDIA as a lead customer partner for their chip designs.
Absolutely. And on that note, Tim, I'm really curious to get your take. From what Amit has just said, semiconductor design teams need to be running very complex, multi-tool workflows that can span for weeks and sometimes even months. Why hasn't this been possible in the past?
Yeah, it's a great question. I think one of the really amazing things about being in this industry right now, and it's been this way for many years now, is that we're in this virtuous cycle of innovation between chip and system design and how that feeds into the ability to create more capable semiconductors and AI technologies that then feeds back into the development of chip and system design. And so as we do our jobs, it's both producing the fundamental infrastructure for the AI revolution, but it's also feeding back into our own technology, which is incredibly exciting. But over the past few years, the focus area of that, and he alluded to a little bit in his answer as well, has been, shifting might be the wrong word, but growing into new domains. And all of them were required to get to this point today of long-running autonomous agents. It started years ago with a maniacal focus on the acceleration of the core tools. The impact of that on the semiconductor design process, I think, is somewhat, it's nice because it's obvious. If the tools run for a short amount of time, you get a result quicker and you get a faster time to market. But then the industry evolved to, as the AI technologies themselves started to mature, we realized that we could apply AI surrogate modeling to those same kinds of workloads and get to the place in some workloads of real-time analysis, real-time insight in the actual simulation of the fundamental workloads of chip and system design. 2026, though, was a really marquee year, and that was the arrival of the long-running agents. These are, the technologies needed to create agents that can preserve state across multiple tools. And I think that's the right definition for a long-running agent. It's not really about how long the agent runs. It's about, is it able to call different tools, reason in between, and make decisions about where to go next while maintaining the state and throughout that process. To do that, though, in a way that's useful, you have to have very fast tools. So it almost feeds back on itself to the previous steps. You need the capabilities to build a long-running agent that can hold context over tool calls. But those agents need to be calling very fast tools, accelerated by AI and then accelerated by accelerated computing. So that's all come together in 2026. We've seen a lot of activity in the area. It's incredibly exciting for the industry in terms of the opportunity it creates for companies like Siemens and our partnerships, companies like NVIDIA, and for the whole world of the industries that build complicated physical things. That's chips, that's systems. It's also airplanes and cars and all these other great products that we interact with every day.
Absolutely. And it's so true. It's all these great products that we interact with every single day. And I think most people, it's not top of mind. So when you're, explaining this to someone that is an everyday user of these, we all are, but of these things, they're like, wow, this is incredible. I also really appreciate your definition of long-running agents. I think that's a really great way where it's not necessarily for how long they run, but it's also about keeping the state and so they can do these really complex workflows.
Well, ultimately, we'd like them to run for less time. So
it's true.
Defining long-running by how long it runs that's counterproductive.
Yeah, exactly. Yeah. What does the underlying infrastructure need to look like to make that kind of long-running agentic operation possible? I know you shared a little bit about that, but can you expand on it a bit more?
Yeah, absolutely. I think that it really comes down to the elements across the three phases of the development of our interaction with this industry and accelerating the industry. It starts with bringing CUDA-X, the CUDA-X libraries, which is our fundamental strategy for accelerating the ecosystem of any industry that we're entering, including chip and system design. We announced some new libraries capabilities here today. Or here this week, as well as a brand new library called cuISS that accelerates the core workloads of chip and system design. That's absolutely essential for a number of reasons. One, because those tools are ultimately the ground truth. The large language model that's used is not running the actual physics workloads, the simulation workloads of chip and system design or any other engineering industry. It relies upon the same tools that were being used before, but accelerated to be at high performance. It's also super essential because the next phase, when we talk about AI physics models, you can't download the internet and train an AI physics model. That's one of the difficult features of AI physics. So you have to be able to do a lot of synthetic data generation in order to build those models. So having very fast tools to do that data generation is essential.
Yeah.
That next phase then is to have the right tools, the AI physics model architectures, the framework and libraries in order for agents even to interact with them and to fine-tune and post-train models while they're in the workflow of chip and system design. And then finally to have a secure runtime model architectures and models like Nemotron that can do the reasoning and work through the process of semiconductor and chip design So all of that comes together now in 2026. We announced the expansion of the NVIDIA Agent Toolkit to include our CUDA-X libraries and the PhysicsNeMo libraries, as well as, of course, OpenShell and Nemotron and Nemo. And our partners like Siemens are integrating those technologies and taking them out to help customers design better chips and systems.
Absolutely. And Amit, given everything that was just described, how is Siemens EDA approaching this with Fuse EDA AI agent? And to even further that question, what makes your approach, say, different from simply layering AI on top of existing EDA tools?
Yeah, so I mean, Tim just laid out exactly the infrastructure part of it.
Yeah.
So we took that infrastructure and applied it to chip design and PCB design with our Fuse launch on Sunday. So first of all, on the GPU acceleration layer with CUDA-X, we have several tools in the Siemens EDA portfolio now that are accelerated with GPUs. So for example, our Slido Spice simulator is getting a 10x speed improvement in the spice
10x
wow. Spice simulation improvement. For our parasitic extraction tools, getting a 10x plus speed up in our parasitic extraction jobs. For our Calibre OPC tools, again, a 50x plus. So that just some examples, and we're applying that across the entire Siemens EDA portfolio to get the faster engines. Then with respect to the release that we made on Sunday about long-running agents for semiconductor and PCB design, what we did was we used the NVIDIA infrastructure, so Nemotron models, NemoGym for optimizing the agents and skills files, OpenShell for security, Switchyard for being able to pick the right size of models for the type of prompt that's been asked. So combining all of that to be able to enable long-running tools across our portfolio. And one example that we showed was for library characterization. So this is typically a several-week job that's done by our customers, and we're able to improve the productivity using agents by about 10x, as well as being token efficient.
Yeah.
You know, that's very important. You don't want to have a huge token bill. So using fewer tokens and using cost-efficient tokens like cost-efficient models like Nemotron, you really reduce the cost of the job by about 10x as well. So that's the kind of productivity boost that we're able to demonstrate in our tools now.
Well, that's huge. I mean, just to reiterate that, significantly less tokens and 10x improvement
In productivity of the engineers. So
in
taking
productivity.
weeks down to days. Yeah.
You have some happy engineers on your hands. Amit, how will agentic AI impact electronic design and engineering teams? You started to allude to that more so with the productivity and 10xing that with engineers. Is there anything else that comes to mind?
I mean, yeah, so productivity is one thing that we're definitely seeing. And as we meet customers here at the DAC show, you know, what we hear is moving design cycle times by 50%. Is what they're looking. So 9 months down to 5 months, or 12 months down to 6 months. That's kind of the high level target, and looking for AI agentic flows to be able to enable that. The other kind of benefit that we see maybe doesn't get talked about enough is really improving the quality of the designs. So looking at power, performance, area, yield of the designs, when you have an agent now interacting with the tools, compared to a human engineer manually interacting with the tools, there's a lot more of an ability to do design exploration, look at what all the possibilities are with the technology that you're using from the foundry, and be able to really push the limits on that design by having an expert agent running the tool now and getting the most out of the design. So I think that's a big benefit that we're seeing that really doesn't get discussed very much, but definitely has a lot of value to push the limits on what's possible at the latest technology nodes.
Yeah,
Absolutely.
Really, I think that's a really important point. You know, when we always talk about performance improvement, and I think the natural state, the way that conversation goes, is about time to market improvements. But if you have a larger time envelope because it takes 1/10 the time, the other option you have is to do a lot more of the work to find a better design and build a better product. And so these things are all interconnected. It's not just about reducing the time, reducing cost, improving time to market, but it's also about building more capable products out the other end and solving problems you couldn't even solve before, because 10x, 50x are such transformative kinds of numbers for all kinds of engineering design problems.
It's so true.
I was just going to say, I think the other layer to that is not just the productivity of engineers, but the kind of skills that you need from the engineers. So now you're enabling junior engineers who aren't necessarily tool experts to be able to work with an agent to be able to get designs out. And that's really one of the bottlenecks in the industry. If you look at the growth trends this year, the semiconductor industry is expected to hit $1 trillion. By 2030, there's expected to be a huge shortage of engineers that are needed versus what's available. So being able to use agents to augment the abilities of junior engineers, intermediate engineers, and senior engineers also, and so that they're not just monitoring a tool, turning knobs. Agents can now be the mechanism to crank the engine, and then they're kind of sitting back at that higher level of abstraction, just like Jensen was saying in the keynote with Roland.
Yeah, it's such a good point, and it really brings it kind of full circle to Amit, what you mentioned earlier in this conversation, where agents are essentially partners now with engineers, and I think it's such a good example too, where it is those junior or mid-level engineers that can really operate so much quicker than maybe they would have been able to without these tools.
Yeah, and even senior engineers, I think they can do more what-if analysis, design exploration. The parallel is with coding as well.
Yeah.
Senior engineers love the AI coding tools because now they can do a lot more architectural exploration, design, and have the AI coding tools be able to do kind of more of that, that operation level work. Same analogy holds with chip design. I don't know what you're seeing.
I don't think any engineer who goes into what chip design or automotive or aerospace is thinking, I want to be an expert in one tool and really be the best at calling the different parameters of that tool. What they're thinking about is a passion for chips and systems. And airplanes and cars and all the things that we build and design. So what agents are going to enable for those engineers is to elevate themselves to the mission as opposed to the task, to be system level thinkers. And so what an incredible opportunity for those industries as well as for ours.
Absolutely. Yeah. And Tim, let's talk about something that I think is on every engineering manager's. Let's shift from the engineers to engineering managers' mind, which is cost.
Sure.
So running AI agents at scale isn't cheap. How are Siemens and NVIDIA thinking about efficiency?
Yeah. So I'm gonna pivot a little bit and try to, because anytime we start talking about cost, I think that it's important to take the bigger picture and talk about value.
Yes.
Because cost on its own is it's kind of uninteresting, right?
Yeah.
If there's no value return, then any cost is too much, and if there's enough value return, then any cost is fine. And so when I think about the value of what's happening here with agentic engineering, it's hard for me to fathom the value and the TAM growth and the opportunity growth across all three layers of the industry, from the platform provider like NVIDIA to our tool and solution provider partners like Siemens, as well as to the engineering companies who use those tools. And I've never talked to an end customer and heard that they have no demand for any increased efficiency or capability in engineering and design.
Yeah.
That's never been the answer. It's always been about getting more. And if I think about what the kind of fundamental limiter is in for those industries, it's really, do you have enough human expert engineers who can use the tools and understand what comes out of them and perform the job? And Amit alluded to this earlier already. So when you imagine a world where an engineer is elevated to a system level thinker and a mission focused engineer who has agents at their disposal to perform these tasks, the amount of engineering productivity and output and value added to those end customers is hard to measure.
Yes.
That also translates down the industry stack for companies like Siemens. If the limit to the engineering output of these customers is the human engineers, it's also the limit to the growth of the tools companies, of the solution providers companies. And so now with agents to do that work and to multiply the amount of engineering output that will be achieved by these industries, it's also incredible opportunity and TAM growth for the solution providers and the companies who are here today at DAC. And of course, because we go to market through those partners, that's true for NVIDIA as well.
Absolutely. I really love how you go ahead.
Oh yeah, I just wanted to add to that. So I completely agree on the value side, and in our customer engagements, when you look at library characterization job, for example, and
Yeah.
you look at the amount of time that takes, weeks or months, you look at the number of engineers that are involved with it, and you factor in the time to market costs of,
Yeah.
and if you could bring that down to a few weeks, or days or a day, that the time to market value of that, there's all that benefit, and really the token cost ends up being a footnote in
Right.
the noise of that overall value. But that being said, we're also focused on working on how can we make it more token efficient as
Yeah.
well. So we are, looking at what are the efficient models that we can be using. What is the complexity of the prompt? Use this kind of sophisticated model for this prompt. Use this sophistication of model for this other prompt based upon that complexity. How can I optimize the skills files? How can I optimize
Yeah.
the product agent? So we're also doing that cost optimization as well, so that the ROI, both the numerator and the denominator,
Yeah.
are improved, so that it gives even more value to the customers.
Yeah, absolutely. I have a question this is for both of you. Maybe we'll start with Amit or Tim if you want to jump in right away. But is there a way to right size the AI being used? Like not every task needs, for example, the most powerful model.
Yeah, I mean that's what I was just mentioning, where we're for example using Switchyard and
Yeah.
model routing to be able to assess, okay, for this prompt, it's a planning type prompt, so I need to have a more sophisticated model, so it'll have a little bit more of a token cost, but then I'll set out what the plan is, and then for more of those micro tasks, I can use a smaller model that's less expensive. So we have that built into the Fuse agent infrastructure
Yeah.
to be able to really reduce and optimize the cost for our customers.
Yeah, I think harness engineering and orchestration is frankly kind of under discussed in the world of AI in terms of its importance. And anecdotally, I think myself and those I talk to about how we interact with agents ourselves, and when we're building our own technologies, we're making decisions about what model to call for different things because we've built intuition about it as human beings. But it's important as we start to provide agentic engineering solutions out to industries that that orchestration is built into those tools as well. And so that's something, of course, that we're working on.
It's always top of mind.
Yep.
Tim, so there's this huge potential for transformation in semiconductor design flows.
Mhm.
And with NVIDIA infrastructure, it's efficient and affordable at scale. But I think a lot of engineers have a question around, or that are watching this have a question around, how do I know I can trust what the agent is telling me?
Yeah. I mean, for engineering problems, it's really important to keep in mind that ground truth doesn't come from the LLM. Ground truth comes from the tools that are being called. The same tools that were being called in 2025 are being called in 2026. Now, they're much more capable. They're more capable because they've been accelerated. They've had AI infused into them. And the agent, of course, is able to reason through and maintain that state and allow that engineer to elevate to elevate their thinking, as we discussed many times already here today. But ultimately, that ground truth comes from the solutions that are built by Siemens, and so that's a really important feature to keep in mind for engineering applications.
Yeah, and I think just to add to that, so yeah, absolutely, all the agents that we're building are it's not predicting the result from an LLM, like Tim said, and giving that. Rather, it's using the EDA engines to be able to give those results to the engineers. So I think that's one point. The agent also is always continuously self-verifying, right? So as when the goal is given by the engineer and the agent is putting together the plan and going towards that goal, then it's in a loop with the tools themselves to be able to generate the data, verify the data, if it's going off track, get back on track using the EDA tools as the source of ground truth. So having that tight interaction between the agent and the tools is very, very important. Having the skills files to be able to guide the agent to be able to do the right things, follow the right recipes is very, very important. Having optimized MCP servers so that interaction is efficient and quick. So having all of that infrastructure in place becomes very important. And that's really added to the offering that we have as an EDA company. Traditionally, as EDA suppliers, we're focused at the tools, and now we're focused, in addition to the layer on top of the tools, all this orchestration and agentic capabilities to make sure that the experience for the customers is very, very good. One other important point there is a lot of our customers who we're seeing, they're building out their own agentic infrastructure. So I often get asked, well, where does our agentic infrastructure come into play versus what they're doing? And one of our main strategy there is to remain completely open. So we're building at our tool level, and we'll tie into whatever the agentic infrastructure is that the customer has and the customer is building out, so that we are experts within our tools and can provide all that value at our tool level, but then we can interact with the customer's agents, third-party tool agents, in order to build out these multi-vendor flows and solutions for our customers.
Yeah, that's a very important thing to note too, because every customer comes with such unique needs, unique infrastructure, that being completely open and partnering with them where they're at is huge.
Yeah, there's third-party agentic harnesses that they're using. They're using not just Siemens EDA tools, but they're using third-party tools. So being able to enable that kind of open, ecosystem is really important. Yeah,
absolutely. What does self-verifying mean in the context of an EDA workflow specifically? I think you spoke a little bit about this with the AI loops and verification in that sense, but how does an agent know if it got the right answer? Can you expand on that a bit? Walk me through what happens when the agent catches, for example, its own mistake.
Yeah, so what we found is we've needed to add additional capabilities at the engine level to interact with agents. So you can think of it as the traditional user interfaces. When a human designer is interacting with the tools, they don't need to know all the internals of the engine and what are the results at that level of granularity. Whereas an agent can take advantage of all that information. So what we've been doing is adding a lot more APIs into our tools so that the agent can get that much more information to more quickly reason, act, check with the tool, get information, feedback loop, and quickly be able to converge on the correct result. So the agentic interface into a tool, we find, is very different than a traditional user interface into the tool, a human interface into the tool.
Yeah, it's something we're seeing across, I think, all software products that we build as well, is that you have to rethink not necessarily the capabilities and the mission of a product, but how do you expose it to an agent as opposed to a human being? And it often unlocks a lot of new capability because through providing skills, you can train an agent to do things most efficiently and have extra knobs available for them. So really, really important. And part of our announcement this week was the addition of skills to our CUDA-X libraries. Additionally, we took PhysicsNeMo, which was a framework for human beings to sort of monolithically train an AI physics model, but broke it up into a set of libraries with associated skills that are really properly suited for either a human, but for an agent to take and to train models, fine-tune models, deploy models. So really a rethinking of how we deploy our software for the agentic era.
And then the other point I'd like to make on that is not making sure that the agent isn't operating as a black box.
Yeah.
But there's a human engineer in the loop. So the engineer is able to see, this is what the agent is doing. These are the steps it's taking. And okay, well, it did something wrong. There was a bump along the way. So then you can augment the agent, right? So you could say, oh, you did this incorrectly. Yep. In the future, do this, this, and this. And then you're storing institutional knowledge for the agent. It's not now sitting with one human designer who knows what to do, but rather the agent now can create the skill for that, and it can be uploaded. And that's exactly what we have with our Fuse agent infrastructure, is a central data lake with our customers that can store these skills files and be able to capture the institutional knowledge of, for this company, these are the kinds of things that I have to know and be aware of. And that's part of the value of being open, is being able to have that infrastructure to be able to capture that information.
Imagine how much faster and larger that knowledge is going to grow when it's captured that way, as opposed to having engineers who are trained and retire and trained and retire, and it's all in that one place that can keep feeding itself and improving the capability of the company. It's incredible.
It really is. It's and what always I have to come back to is a lot of all of the announcements we're speaking of today are just recent announcements, and they all feel so big because they are. But kind of what you were alluding at, Tim, it's moving so quickly, and we're solving such big challenges quicker and quicker as well, which is pretty exciting. let's talk about reinforcement learning, where the AI improves through repeated experimentation and feedback for anyone watching. Something that's new to EDA, though, is this something that's new to EDA, or has it been happening for some time?
So machine learning, reinforcement learning techniques have been around for around 20 years. I mean, obviously the methods themselves have been improving, but I founded a company, Solido Design Automation, where we were still using reinforcement learning for custom IC verification.
Okay.
So the idea is, for example, if you're doing a Six Sigma verification, if you're doing a brute force Six Sigma verification, that would take 5 billion simulations. So what we did was we developed a system where there's AI in the loop of the SPICE simulator, where it'll run a few hundred simulations. It'll build a predictive model out. Then it'll predict out the Six Sigma points, and it would self-verify. So then the AI would go and run brute force simulations at a few of the points to make sure that the model is correct. And if it's not correct, it'll run more simulations. And if it is correct, it'll give. So the net value was we're able to take the number of simulations down from billions down to a couple of thousand simulations. So, and this kind of machine learning, reinforcement learning techniques are now within the engines of all of our tools in Siemens EDA. But it's an area that we continue to focus on as technology is improving. Physics AI capabilities are improving. We're constantly seeing how can we speed up the engines themselves to be able to get results faster using AI techniques. And the nice thing is, all the investment that we're making, like you were saying, Tim, at the engine level, that productivity improvement multiplies with the capabilities that we have at the agent level. So it's not like we're taking the eye off the ball at the engine level. That's still extremely important, and we're doing the agentic side of things.
Yeah, that feedback, it's a really interesting kind of microcosm of the bigger picture of the virtuous cycle. Right, where chips and system design results in better AI, results in more capable chip and system design. But you see it at kind of every level of the stack. You see it in the tools as Amit was describing. We're also seeing that and investing that within our libraries themselves. So we announced cuISS, our iterative sparse solver library, here at DAC. And one of the things that we're looking at is actually having an AI learning in the loop of these solvers, which can reduce the iteration count by 3x. That's a multiplicative 3x on top of the performance improvement of making the iterations faster. So across a suite of applications, as that gets integrated in there, that AI is going to actually improve the solvers within the applications, which have that same improvement already being built in as you described. So there's layers and layers of how AI is infusing throughout the stack and improving the capability of chip and system design. It's really, really exciting.
It is. Thank you for that. And I'm sure people watching this right now, or even on my mind, one question that comes up is, we're speaking about these really incredible innovations. Amit, you mentioned as well too that when it comes to machine learning, reinforcement learning, it's not something new. It's been around for years and years. So why has it taken until now to get here? And what's changed in the last 12 to 18 months to make this all possible?
Yeah, I mean, so machine learning, reinforcement learning, that's something that we've been infusing in our tools, and customers have been seeing the benefits for years. So that's not a new thing. What's happened recently is large language models, and what that's unleashed, and now with agentic infrastructure, what that's unleashed. So there's basically new tools in the toolbox, or new superpowers that have become available that we're now taking advantage of from an infrastructure point of view to deliver to our customers. And we're talking before about what is DAC next year going to look like, and what are the new capabilities? And I think right now we're building out at the tool level the agent capabilities. So custom IC design and place and route and design for test and digital verification. And I think what's going to be interesting next year is when you're starting to combine these domains together. So taking it from high level synthesis to digital verification to place and route to design rule checking to fixing those design rule violations and doing a whole custom IC design verification. So being able to have more of these top level agents and Fuse Agent be able to orchestrate the product level agents to be able to come up with solutions. So increasing that level of abstraction, I think, will be the trajectory next stack when we're here together.
Kind of the amazing thing, I often talk about how once you know how to do something, it transitions from science to engineering. But if we look a year ago and we tried to say this is where we'll be this year, I think that would have been science fiction, not
Yeah,
science,
yeah.
right? It really didn't. We talked a lot about agents, but we didn't really have a path to this idea of a long-running engineering agent.
Yes.
Part of the reason for that and how fast it's moving is just all the different parts of the puzzle that had to come together. There was a lot of work involved. But the really big one in 2026 to me is the orchestration layer, the agent infrastructure that created the ability to have long-running agents that are able to move through things and keep context. And that was really groundbreaking for, I think, for all industries this year. The idea of long-running agents being practical. So from here, I definitely agree with Amit. We're going to see breadth. You're going to see the continual addition of long-running agent capabilities across different parts of the design workflow. But then it's going to start elevating and go vertical, and to have agents which are able to think across the design process. So next year, I'm sure we'll be talking about that. But also, like I said last year, if you had asked me, we wouldn't have said this. So who knows?
I know.
Who knows?
It's fun to speculate based on, where everything's headed, where
Yeah.
the data is, what innovations we're speaking about today. But as you mentioned, it sometimes would feel like there's no way, or it's
Yeah.
science fiction, even as two individuals who work on this day in and day out. Yeah. I want to, so we started to zoom out a little bit, talking about what next year might look like even as well, too. What, for Amit, question I have for you is, what milestones will indicate we've genuinely moved beyond automation into trusted agentic engineering?
Yeah, I think it's trust with AI is extremely important, obviously, because now you have AI doing tasks that typically humans were doing. So, and we've gone through this journey with machine learning and reinforcement learning as well. So how can we get user trust? And when we were first getting started back in 2005, there was a lot of skepticism. Can I trust this for taping out my design and signing off on it? And the way we built trust with engineers is really around giving transparency into how the AI is operating. What's going on under the hood? How is it converging on predicting results? Where is it going wrong? Okay, it's predicted out this 5 sigma point, for example, back to my previous analogy, but that doesn't line up with the simulation. So it's going to go and do another building of the model based upon some more data. So giving that level of visibility and transparency to the engineers, we found really builds that level of trust for them to trust the results. Now in the area of agentic AI, it's all about leveraging the core EDA tools. So making sure that everything that's getting generated can be verified with the core tools, and making sure that there's that visibility to the engineers so that they can have that level of trust and sign off, and they go into a design review and say, hey, this is what the agent did. These are the steps that it went through in order to come to this result. It makes sense. It's validated and verified against Calibre, so that kind of visibility, I think, is what's very important to get to that, trusted outcomes.
Yeah, no, it's true. It's visibility really nowadays. I think especially for engineers equates to trust. If you can see what's happening, the steps taken, that it's a good handshake.
Yeah, exactly.
Before I let you both go, if someone's watching this that's an engineer who's been maybe skeptical of AI hype, I'll put that in quotation, what's one thing you would want them to walk away from this conversation understanding, or feeling really excited about, or maybe changing their perspective or opening their perspective a bit more? Tim, I'll start with you.
Yeah, if I can do two, I'm going to
Okay.
do two. So, the first, I think, is we've touched on it a couple times, is that in agentic engineering, ground truth comes from the tools.
Yeah.
And so we're not asking the large language model to solve the fundamental problems, the workloads that the tools are doing yet, that we're doing last year and we'll be doing this year and on into the future. And so, understanding that, I think, reinforces the idea that this is the right direction. But the other is, that saying that, when's the best time to plant a tree was last year and the second best time is today. We're still in day zero. So it's last year right now, but it's not going to be there for long. So the most important thing for engineers who are watching this and interested or skeptical is to jump in. When we watch the development of trust in AI physics, which I think started in late 2024, I think one of the one of the reasons that happened was AI started to permeate the other parts of our lives. And so as you start to interact with any technology more and more often, you get more comfortable with it, and you start to look for how it can interact with other parts of your life or your work. And so it had a big impact on the interest and trust in developing AI surrogate modeling for those business workflows. So jump in today is how you get comfortable with this idea of agents, and go build your own agent at home and see how that feels, and how it helps you with tasks around your house. And that kind of firsthand experience with this, I think, will help people see how exciting and transformative this moment is for the engineering industries, because I think that we're at the start of a change the like of which we've never seen before for how companies engineer, design, and manufacture the most complicated physical equipment in the world.
Absolutely. And I want to, on that, what you just said, Tim, something really came to my mind, which is Jensen once said something that really stuck with me. I'm a visual learner, and I think it really goes well to what you just said, which is, if you're outside of a train and you're watching it pass by, it looks like it's going so fast. There's no way you can be part of it. But when you're actually on that fast moving train,
it can be quite comfortable.
It can be quite comfortable. I mean, it's still going pretty fast, as we know, but it's much more comfortable. So what about yourself, Amit?
Yeah, I mean, I was going to say too, just be hands-on with the tools. Don't just like read all the news and the announcements and so on, but just try it, right? And in the context of EDA, everything that we're doing for agentic workflows, just try it. Evaluate it, see how it improves your productivity. What's good, what's bad. How can we improve it? And we're really partnered now with most of the leading semiconductor companies now with their designers to be able to deploy Fuse, work on various workflows with them to be able to show the value and also get feedback, right? And we're in a tight feedback loop with our R&D engineers. They're saying, it'd be really good if we could make this automated and be able to take that feedback and turn it around in product. I think that's really useful, but I encourage everyone just be hands-on.
Hands-on. It's the best way to learn. It's some of these things can feel intimidating, but when you start exploring them and as I like to say, trying to break things, which you always learn the best way from, it's the way to go. Well, thank you both so much for your time. I was really looking forward to this conversation, and I'm leaving it just feeling really inspired and excited for not only what's here today with these announcements, but what's to come. And thank you all for tuning in. We're going to take a short break and come back, and we're going to go even one layer deeper with some tech deep dives on this. Hi, everyone. Welcome back to the Siemens and NVIDIA live stream. We're here at DAC today. And if you're just tuning in, my name is Tiffany Jansen. I'm a software engineer and founder of Tiffin Tech. And today we are back. We're back for more of the technical deep dive. And I'm joined by Niranjan/Niro Siddhapur, and who works at Siemens EDA. And then I'm also here with Josh Mayberry, who is from NVIDIA. Before we get into the questions and deep dive, I'd love to learn more about what both of you do. Niro, let's start with you at Siemens.
Yeah, no, thanks, Steph. Excited to be here. I work as the central AI product manager for Siemens EDA. So mostly work on productization, go-to-market for agentic AI, but for engineering workflows. So, and that kind of tees up with my background in AI and engineering. So it's been pretty fun.
Yeah, thank you for having me here. My name is Joshua Mayberry, and I work at NVIDIA as a senior product technical lead. So I work with our EDA partners on adopting our AI libraries. But it's not a one-way street. It's not like just us presenting, hey, here's the the menu of options. It's very much a two-way partnership. So we work very closely with Siemens EDA as a design partner, bringing them early into AI library development, gathering feedback from them, and then iteratively refining those libraries so that they become more and more useful for Siemens use cases.
I think that's such a good point you made, Josh, is it's not just a one-way partnership. It's a collaboration almost, is I think how I would describe it.
Yeah, and what's really exciting too is that I work closely on our NeMo libraries, which are used for evaluating and optimizing agents, and a lot of that work actually happens in open source. So if you want to know like what are Niro and I up to, you can go to GitHub and see, our roadmap, see the feedback we're getting in real time. So there are no secrets.
Really
It's
cool.
very open. It's very collaborative. It's a lot of fun.
That is a lot of fun. So for any engineers watching this, you mentioned they can literally just go to GitHub and see what you're working on. What repository would they go to? Where are they going?
Yeah. So I think you heard Tim and Amit reference work we've done using NemoGym.
Yes.
So NemoGym, as the name implies, is a library for training and evaluating agents. And so when NemoGym first started, right, it was primarily used as a distributed runtime for training language models, right? It integrates very closely with those RL frameworks. However, in the last year, the world has changed, right? When nobody just wants to chat with an LLM anymore. It's actually about, using an agent that has state, can execute long-running tasks. And so NemoGym has been evolving to support evaluating and optimizing agents. And so there's been a lot of work that we've been doing in collaboration with Siemens to make it, fit for this new purpose.
Absolutely. This question I want to start with is for both of you, but Nero, I'll start with you. The fundamental challenge that you're both trying to solve is EDA workflows aren't quick tasks. They can run for days, weeks, sometimes even months. What makes building an AI agent for that kind of long-running, high-stakes, no pressure, high-stakes environment so much harder than, say, building a chatbot?
Yeah, no, that's a great question, and I think it's a couple of buckets of things. One is just I like to say like EDA workflows or chip design or any engineering workflows are like multi-step, multi-tool, and iterative. So it's multi-step because it's like imagine building a very elaborate cake,
Yeah.
which has so many different recipes that you have to do and so many different components and ingredients. And so you need a very long list of exact things to follow or cure it at this temperature only for this much time, this kind of things. Oh, when I say multi-tool, it's like tool is like the software for simulation or anything. So most of the times for chip design, you'll have 5-10 softwares being used at a minimum throughout the chip design, or maybe even more. And they reside on different compute clusters. They reside, different people are experts in them. So coordinating all across all of them, it's difficult. And the third thing, I said it's iterative, right? You make a mistake, you have to go back. And so as compared to say like, oh, can you wipe code me this dashboard?
Mhm.
And you have a purple looking dashboard because that's what most of the LLMs like sometimes. This is much more difficult because of the steps, the tools being distributed, and the iterative nature.
Yeah.
And then coming last to the high stakes part is a lot of the chips are at a very tight schedule, like market scale. Like you want your new iPhone in September
Yeah.
or during WWDC. And so if the chip for that new iPhone A19 or A20 is not made properly or it's not designed, it's going to delay it, which is like $300 million of loss or maybe more. So that's the stakes.
It's very high stakes.
Yeah.
But good thing we have both of you who are experts at your jobs. Josh, I would love to get your take on that as well.
Yeah, so I was thinking about it from a slightly different angle. When you think about a long-running agent, right, a lot of us first became familiar with this through personal assistant use cases. Like, who doesn't want to have an agent that helps you check your email, triage your calendar, and I think that gets everybody excited, right? It's very easy to fire up, an OpenClaw or Hermes and have this helpful assistant. Now, what's easy about that world is that you're mostly integrating with web services, right? And so you have an agent, you point it to a few endpoints. It's able to pull in small amounts of data. And really interact with these services in a pretty secure way, right?
Yeah.
Because that application interface was designed around that paradigm. But now when we think about EDA, what we're really thinking about is scientific computing. And so if you think about scientific computing, a lot of your most valuable work, lies in what's called scratch space, right? And as the name implies, scratch space is supposed to be meant to be something that's ephemeral. And it's an area where engineers can stage, analyses and design files. And so these systems were designed to be used by engineers, and primarily they were driven, historically by scripts that were, carefully written and tested, all very manually, very iteratively. So you bring an AI agent into this environment,
Yeah.
and there are a lot of things that that can and will go wrong, right? From overloading your compute cluster to potentially deleting sensitive files or sharing them in either to people or in repositories where they weren't meant to be shared, and there's a regulatory aspect of that as well, right? A lot of this data is export controlled or highly proprietary, and so it's not obvious how you bring an AI assistant that was trained to be good at checking your email to now be really good at handling very, very large and very sensitive files.
So how do you, it's a huge challenge that you have to navigate. And how have you seen, like, expand on that a bit more? How have you faced those challenges with that? Like you mentioned, that's not maybe what it was designed for. So then now with how you're utilizing it, how have you found overcoming those challenges?
Yeah. So, in NVIDIA, there we have this concept of power users, and it's kind of funny because you think power users, you might think of a select few, right, that are of engineers that are really utilizing the AI tools to full extent. But in reality, it's pretty much everyone, right?
Yeah.
We're all utilizing AI in our day jobs, and nobody wants to restrict or slow down the pace of innovation. And so, I think most organizations in early days are accepting of some risk, right, and then trying to identify, through iterative learning, okay, where are the risks unacceptable? What do we need to do to tighten our security posture or make these agents more reliable? And it's a holistic exercise. It's not one where you can just write up one declarative policy and call it done.
Yeah.
Right?
Yeah, absolutely. It's, as you mentioned, both NVIDIA and Siemens are huge companies, but I feel like, speaking to the both of you, even just throughout our conversation thus far, and even to the conversation previous, you have to have that startup mindset where it's iterate quickly, fail quickly, fix quickly, grow quickly. It probably feels like that as well for the both of you.
Yeah, that's true. And what we have seen with working with these early customers or our pilot partners is we'll start a project with them, and we'll say, okay, in 3 months we're going to get this done.
Yeah.
And 3 months comes and the goalpost has moved.
Yeah.
We started with Fuse, which is our central AI system, last year at Design Automation Conference, so exactly 12 months ago. That was my first year with the company, and then everything was about co-pilots and Gen AI agents, and everyone just wants to have a chatbot, which is sure, it's useful. And then we were like, okay, let's set a timeline for 3 months. After 3 months, MCP came, and everyone's like, okay, I want MCP now. And then you said, okay, that has a bunch of things we need to figure out: how many APIs to expose, how many tools to expose, so not to saturate the LLM and things like that. And it took some time, say a few months, and then a few months later, you're like, okay, now we're great. They're like, oh, skills came up, and now again it's saturating the context window, much more possibilities, but also much more difficulties. And then, as Josh was talking about, is okay, how do you bound it, right? It's the sandboxing of it, where you don't want an OpenClaw type EDA agent just putting your IP on the internet so that everyone else can copy. Or more realistically, it's also about the whole chip design flow is multi-step, as I was saying, and each of those steps have experts. And if you are customer X or company X designing chips, you don't want team A in that first part of the workflow, their agent doing something that affects team C, because every skill or MCP server is available to anyone. So there has to be even more internal access control, if you will. So we are part of the same company, but there's still some compartmentalization, because I don't want you to change a file that's already been iterated on by mistake.
Exactly.
Yeah.
Exactly. Josh, I want to talk about how to actually build these trusted workflows. I think when you both know better than anyone, something that's always on engineers' minds is around trust. So if I'm an engineer and someone tells me an AI agent is going to start making decisions in my design flow, my first question is, how do I know it's not going to do something, to what Niro was mentioning as well too, catastrophic, if you will? What is the answer to that?
Yeah, so the answer to that is having a robust evaluation strategy. And so as we've moved from building these co-pilots, like Niro was saying, couple years ago to building autonomous agents, what we're really doing there is we're working as one team in one environment, and we're taking a very rigorous approach to codifying these workflows in a reproducible evaluation environment. And so when I mentioned Nemo Gym earlier, that's really the value of Nemo Gym, is being able to capture everything about the state of the world when the engineer comes to their computer. So we have, all of those design files, staged right in a repository. We're giving the agent access to the tools it will have on the job. And so then what we do is, we replay these scenarios many times, because as we all know, right, these LLMs are stochastic. You're not going to get the same result every single time. And so, we will test across many different scenarios, right, to sort of see how the agent behaves. And you might say, okay, that's great, but I mean, what am I going to do now? Am I going to just sit and eyeball the results? That's that's not scalable. And so what we've done this year is we actually tried to pick problems where the labeled data already exists, or trusted data already exists. Right. And so our first use case, Lighthouse use case that we picked for a long running agent was this Slido, based on using the Slido Characterizer product. And I think Amit talked about that a little bit earlier. Mm-hmm. I don't think he went into detail about why did we pick that.
Let's go into detail.
I mean, you don't have to ask me twice. Cut me off if I'm running long. But the really great thing about that use case is that foundries are releasing PDK updates every few months. And so what that means is the engineer who's characterizing standard cells is repeating this analysis every few months, and they historically have needed a way to compare an older reference library to a new one to make sure that the timings and power requirements stay similar. And so Slido actually has a lot of really great analytical tools where you can point, library A, library B, and you get a structured report that's telling you, are these similar outcomes? And so having these types of traditional analytical tools has enabled us to build really robust evals and not just rely on like an LLM as a judge.
Absolutely. No, it's a huge differentiator. One thing, Niro, we're speaking a lot about EDA workflows, and before we started this conversation, you took me through a diagram, which for me as a visual person, it really hits home. So throughout this conversation, when it's time, when you're like, this is a good time to pull up the diagram, you let me know, because I really want to show the viewers as well about this diagram.
I think, Ryan, do you want to pull up the diagram? That'll be great. Thanks.
So Niro, you mentioned, the diagram's up, that EDA workflows span many tools, many files, and compute environments. What makes orchestrating all of that with an AI agent so technically difficult?
Yeah, no, that's a great question. And as you can see on the diagram, basically, your AI agent has access to many tools which can be now exposed as MCP server. So imagine each tool is basically a software. It has, say, few MCP servers and multiple tools. So like, say you have 10, 20 MCP servers. Each of them have bunch of tool descriptions. So it's like, say, 10 into 1000 or 20 into 2400. And then it's also skill files. Like, this is the guidance, right? Like the MCP tools are like the API calls, but the skills is the guidance. And so you have a bunch of skill files. It's not one skill.md, right? It's a progressive disclosure. So it's many of them. So essentially, when you load up all this into the context of any LLM or agent, even if you have a 200K context window, it's going to saturate.
Yes.
So that's one. The second is, many of these software tools will say, simulate this, simulate that, analyze this, analyze that, which means that a lot of these tool descriptions and skills, from a semantic point of view, find similar. So now the agent is kind of confused, like, oh, simulate this, simulate that. So because it's stochastic, as Josh was saying, sometimes it will go down this route and sometimes it will go down that route.
Yeah.
All the routes may not lead to the top of the mountain. And so that's another thing. And the third thing we were talking earlier is these different EDA tools or softwares, because they are also compute heavy, like Amit was mentioning, right?
Yeah.
Engines itself take weeks and days. They need GPU acceleration. They are on different compute clusters.
Yeah.
So I can't be just on my local laptop and have an agent communicate across all these different tools and different clusters. And so logistically, it makes it difficult to do it. I can keep going deeper, but that's like 3 buckets of problems, if you will.
I like that. I'd love to go a little bit deeper too with those 3 buckets. I mean, even you mentioned at the end there, the challenges logistically. How do you solve for that?
Yeah, so that's a great question for like the EDA environment
Yeah.
things. Like, so what our approach with Fuse Agent was, um, uh, I'm gonna go technical, but let's see how it goes. So imagine you have Chip Designer 1, Chip Designer 2, Chip Designer 3. They have their own local environment there with their own local Claude Code, Codex, whatever is your favorite
Yeah.
IDE, Cursor, VS Code, doesn't matter. It has access to certain scale files, MCP servers, and so on. But now local environment 1 can't talk to local environment 2. So we need something that is server side on, as a central gateway, if you will.
Mhm.
And so with Fuse Agent, that's what we built. We built like that central gateway. That's like a unified MCP endpoint, a unified repo of all the skills. So it becomes like a USB-C dongle, like a central
That's a good
place.
descriptor.
Yeah.
Uh,
And because it's server side, so Chip Designer 1 in Team A can send the query, like the agent can send the query to the server side, go to, local environment B, go back to local environment C.
Yeah.
And so now, the pipeline can work. So like that's a good mental model to have.
It is. You said when you started going deeper, you said, let's see how this goes. It went well. Those descriptors were very, very clear and easy to understand. So thank you for that. Josh, is there anything else you want to add to that?
Yeah, so I think one of the recent examples we saw of what can go wrong here with so many tools and so much complexity is
Yeah.
that the agent oftentimes will try to take the most expedient path, and so
Mm.
and so we might think we've written a good skill file that it's going to be obvious to the agent what to call that skill, to access the right MCP server, to call the tools in an efficient manner, but the agent may not see it. And so when we were doing some of this optimization work, what we were seeing as we did these collected rollouts with Nemo Gym is that actually oftentimes the agent was going around these MCPs. It was trying to make direct command line calls to some of these tools and making a lot of mistakes, right? And so that's burning up wall clock time, it's burning tokens. And so by analyzing these failures, the engineers at Siemens were then able to write better skills, better MCP server descriptions, so that success rate went up, right? And we were able to kind of close off this failure mode.
Absolutely. So what you're saying, Josh, is the agents just want to take the easy way otherwise.
Yeah, and I mean, they're tested too. I mean, what do you think agents are really good at? They're really good at building websites. They're really good at, writing a simple Python script. And I don't, because I don't think that much post-training is happening in EDA environments today. They're just not aware necessarily of the cost, right, of some of these
Yeah.
tool calls.
Absolutely.
Yeah.
Absolutely.
I would love to elaborate on that. I think Ryan, you have another good visual where, like the flow that I was trying to explain, how we were working with Nemo Gym to help. So like the flow you can see on the screen has like multiple steps. So imagine like you have to set up the simulation in the right manner. You have to test if it actually runs on this compute cluster somewhere in another country, maybe.
Yeah.
And then we use some machine learning as well. So make the local model, use the local model to do some prediction. So there's a bunch of steps, and then this whole process might take, if you give a prompt, it might take 1 hour, 2 hour, 3 hour, 4 hour, because some of that time is also like the actual physics simulation. In this case, like it's called SPICE simulations, or which is like transistor level simulation, which can run on 1,000 cores or 500 cores, CPU cores, which is different than like the LLM running on Azure or
Yeah.
AWS or whatever, right? And so with Nemo Gym, what were we able to do was we started with this like mega scale file and 2 MCP servers, which were like, okay. And this same process used to take 8 hours.
Yeah.
And then we would analyze with Nemo Gym, like, where are those pain points? Like, where is the agent getting confused? As I said, like, semantically, the tool calls are similar, or maybe the instructions are not clear enough.
Yeah.
And we tried to do this few times, and we could get down from 8 hours to around 2 hours.
8 hours to 2 hours.
Yeah.
And I think one of the things that was really fun about this partnership is we had brought in the product manager for Gym to kind of teach the combined team some of the best practices. And as we were going through that flow, we were realizing that, after the team collected these rollouts, right, all these histories of the agent interactions, they weren't there wasn't the most obvious way how to analyze them, right? And a lot of it's easy to do it ad hoc. You can ask, Claude Code or Codex,
Yeah.
hey, what's wrong here? But what we know as practitioners, especially building our Nematron model, that there are actually much more intelligent ways to query and try to do causal analysis. And so we were able to bring in a causal analysis skill that we had been using on the research side into the library, and we were able to do that within a couple of days. And so that handover, within less than a week, right? We've taken working knowledge from our research team and put it in the hands of the Siemens engineers.
Wow.
And then now that skill, is out. It's out in GIM. It's available for anybody to use. But I think sometimes, it's helpful to have that nudge from our partners to bring things, from research out into production so that others can benefit.
Yeah.
Absolutely.
And that really helped because not only did it cut down the time, but also because now the flow is more tighter, if you will.
Yeah.
It's still flexible, but
Yeah.
more tighter.
Yes.
You have, since you were talking about tokens earlier, it's 25% more token efficient, and which means less token
Yeah.
costs. And I think last year we were in the era of token being abundant, and now we are getting to the era of token conservativeness.
Yeah.
So that's good to see.
I also wanted to call out here too that prompt evolution isn't a new topic, right? There have been many algorithms developed, to help people develop better prompts. And I think, as engineers, it's very tempting to want to build a black box optimization engine around that and, burn more tokens, burn more time, more weeks
True.
optimizing everything. And I think, where I think did a good job here was kind of recognizing the benefit of a very pragmatic approach to optimizing agents and getting those benefits into our hardware engineers' hands very, very rapidly. So this isn't just innovation theater. We're actually shipping these refined agents.
I've never heard that term before, innovation theater, but I'm going to steal it from you. But to your point, that's not what's going on at all. It's so funny. I know we have a limited amount of time. I think I have 100 other questions for you both, just because it's so fascinating what you are working on, the problems you are solving. But I'm curious to know, Josh, I'll start with you. For a company that's just starting to deploy agents, someone who's watching this, how do they even know which tasks are quote unquote easy versus complex in terms of model requirements?
Yeah. So in terms of knowing what's easy or what's complex, I know Amit referred back to model routing. So a lot of people right now, they want to know what's easy, what's complex, what can I send to, very expensive frontier model versus what can I process with a smaller open model, for example. The only way really to know is to own your evaluations. Nobody else is solving the same problem in the same way as you. And, you can take, for example, a classifier model that's, it could be an LLM. Somebody has trained it to decide what's easy and what's complex.
Yes.
But what's true in one domain may not be true in another. And so we've done some early experimentation, for example, with model routing. And what we find is, you have to teach the model how to recognize these tasks. So if you're using an LLM classifier, that might be writing a prompt that recognizes all these proprietary skills and tools, or it could be training a classifier where you actually observe how well a model does on different types of tasks, and then using that you can train a classifier that will appropriately route each prompt.
Yeah. No, it's really it's very unique and customizable based on what different customers are coming to you really for. To wrap up, Niro and Josh, Niro, I'll start with you. What's one thing you wish more people understood about what you're building that maybe doesn't get talked about enough?
I think it's about just trying it out. Like, I feel like with engineering workflows, whenever we talk to customers or users, is because it's very deterministic, they have this inherent activation barrier, if you will, of like, oh, LLMs are stochastic, so how is that going to work? And then my only advice is like, go just try it out, and I'm sure you'll get hooked onto whatever is your favorite coding IDE, or just try to play with it, and then you can start to improve.
Absolutely.
So I'm sure some people out there saw the recent comments from Alex Karp, the Palantir leader, about trust and who do you trust with your enterprise data. And I think when I look at our partnership between NVIDIA and Siemens, that level of trust is extraordinarily high. So when we were scoping this Lighthouse use case, we wanted to send to Siemens some test cases, which include NVIDIA's entire proprietary standard cell library. We send an email to our leaders, and we have approval within, minutes.
Wow.
And that data is transferred within the day. So that level of trust, which has been built up over decades working with our EDA partners, that is hard to replicate. And I think, while there are many companies that have, ML or AI expertise, you have to ultimately be able to trust somebody with your most valuable data.
Absolutely. It's funny that we're ending on that, because I'm pretty sure how we started the conversation was around how engineers value trust so much. So I think that's a great way to end the conversation. Josh, Nirav, thank you so much for your time today. And thank you everyone for tuning in. This is going to be up on YouTube afterwards. So if you didn't get to see the full conversation, you can tune in afterwards. Thank you all.